Let's see. Number 1 is domain. What's the domain of that function?
Negative infinity.
I see one thing I can't let x be.
Oh, that's right.
Can't let x be 0. Everything else is okay. Number 2, what about y-intercept? That would be letting x be 0, and we just said we can't let x be 0, so this graph doesn't cross the y-axis. It may cross the x-axis, but I'm probably not going to ask you that. Number 3, what about asymptotes? What do you know about vertical asymptotes?
Would be 1 at 0.
X equals 0 is a vertical asymptote. Horizontal asymptotes I'm really not going to recognize unless I write that as a single rational expression. My whole theorem on rational asymptotes is dependent on having a single rational expression, then looking at the degree of the numerator and degree of the denominator. So I'd have to multiply this by x squared over x squared to get a common denominator, but then I'd have x cubed plus 32 over x squared. And I can see that the degree of the numerator is 1 more than the degree of the denominator. So what does that tell me about horizontal asymptotes? There is no horizontal asymptote.
But there is a slant.
But if the degree of the numerator is exactly 1 more than the degree of the denominator, there's a slant asymptote. Or some books call it oblique asymptote. How do you find that slant asymptote? I probably typed it for you. Probably. Slant asymptote with the equation y equals ax plus b, that's just a line, where ax plus b is the quotient of the numerator divided by the denominator. What does that mean I need to do?
Let it equal to x squared.
I need to divide the denominator into the numerator. Well, actually, I'll show you and then I'll show you something faster. All right? If I divide that out, actually there's no point in even doing long division because I'm only dividing one term into 2 terms. I would get this back. And this is the quotient, this is the linear portion, so my slant asymptote is just y equals x. Now what note can I write you so that when you get home you'll know why we did that? I'm going to say that's the quotient when x cubed plus 32 is divided by x squared. On a different problem, you may have to use long division or synthetic division, both of which you're supposed to know, but if you get stuck, you can email me. Anytime you divide a 5th degree by a 4th degree, your quotient's going to be 1st degree. Or 99th degree divided by 98th degree, the quotient's going to be 1st degree. That 1st degree quotient is always your slant asymptote. This 32 would actually be the remainder, and we always put the remainder back over the divisor. Just the x is the quotient.
So it wouldn't be y equals 1, not x.
No, it's not a horizontal asymptote. It's a slant asymptote. Y equals 1 would give me a horizontal line. All right, so slant asymptote, that covers all the asymptotes.
So asymptote,
I know why it can't be 0.
I'm looking at what?
ax.
Well, it's 1x plus 0. I mean, I could write that in slope-intercept form. The slope is 1 and the y-intercept 0. And when I get ready to graph, I can actually go ahead and graph that slant asymptote now. There's a vertical asymptote at 0. There's no way I can go back in and dash in the y-axis. The slant asymptote y equals x has y-intercept 0, slope of 1. So that's my slant asymptote.
So why didn't you do the plus b part again?
Because there is no plus b. Sometimes if I divided, let's say if I had x cubed plus x squared, then when I divided, I'd have a constant on the end. But here, I just didn't have a constant.
Okay.
All right, let's see. Number 3 is everything you never wanted to know about asymptotes. Step 4, it's time to find derivatives. Now, again, I know that you know the quotient rule. So if I can find where I wrote the derivative, I'm not going to redo it. Right here, I got the first derivative to be x cubed minus 64 over x cubed.
Would you have done the quotient rule on the one term combined, or would you have done it on like x plus?
Well, if I differentiated this, I could use the quotient rule. If I differentiated this, I could just say, write that as x plus 32x to the negative 2. My answer would have been 2 terms if I had not used the quotient rule, but once I got a common denominator and put it back together, I'd get the same thing. So it's kind of where you want your work to be in the calculus or the algebra. All right, so what are the critical numbers?
And the x cannot equal 0.
I was tempted to say 0 and 4, but why is 0 not a critical number? Because it made the original function undefined. So just to make you a note to look at at home, the critical numbers could be 0 or 4, but the 0 makes the original f of x undefined. So my only critical number is 4.
I finally get that now.
Good. So I'm going to look at the sign of the first derivative to the left and to the right of 4.
Do we care about the vertical asymptote?
There is a vertical asymptote at 0. There will be graph to the left and to the right of 0, but the sign of the first derivative is not going to change at 0, so it really doesn't matter if you put that on your number line or not. You're better off having too much on your number line instead of too little, but if we chose negative, let's see, what did we say, that's 0? If we chose negative 1 and positive 1, we would get a negative divided by negative 1 cubed.
Would be negative minus negative over negative. So
Negative 1 would give me a negative over a negative. Holy cow, Sarah. Yes, ma'am. We need that. It's not optional. We needed that vertical asymptote on there, and the sign does change at 1. It just can't be a relative max because it's a vertical asymptote. When we let x be 1, we'd have a negative divided by a positive as a negative, And when we let x be 5, we'd have a positive divided by a positive is a positive. So absolutely, if you have vertical asymptotes, or if you have a restricted domain, like if I couldn't let x be anything more than 6, I would have put a solid line at 6 just to make me cut off there.
But you wouldn't put the horizontal on the X of them.
No, horizontal asymptotes are constants from negative infinity to infinity. I'm only looking at x values right now. All right, so I can answer parts A, B, C, and D.
If the function, the original function, if it had a square root, does that mean x can't be a negative number because it couldn't be imaginary?
You can't. That's not technically correct, or that's not quite precise enough, because what if I had square root of x plus 5? I could let x be negative 4. So you don't want to say x can't be a negative. You want to say the radicand can't be negative.
Okay, so that's where the limit of x would be, or you'd have to put another line on the.
For domain, I would have put negative 5 to infinity, and on my graph, I would have put a solid vertical line at negative 5 to indicate I couldn't go beyond that.
Right.
So
okay.
that's why I use solid lines for endpoints of my domain, but vertical lines or dash lines for asymptotes. I can be on either side of an asymptote. Also, if I had a logarithmic function, that domain, could I let x be negative 5? I can take the square root of 0, but I can't take the natural log of 0. So here I'd have a parenthesis on the negative 5 to infinity. But I'd still put a solid line to keep me from going to the left of negative 5 on my number line. Okay?
Okay.
Alrighty. Good. So let's see where it is. A part is increasing, B part is decreasing. Please put these words on your homework so it'll be easier to grade. Otherwise, I'm going to have to keep looking back for reference to see which one's increasing, which one's decreasing. C is relative max. I'm sorry, what?
Shortened versions of the word is cool, right?
Yes, if it starts with a I, I'm going to assume it means increase. And then relative min. Where is the function increasing?
Negative infinity to 0.
Negative infinity to 0 and 4 to infinity. Where is the function decreasing? 0 to 4. Are there any relative max?
Yes. 0, wait. No, wait.
It would be at 0 if there wasn't a vertical asymptote there. But since there's a vertical asymptote at 0, there's no other place where the function goes from increasing to decreasing. And then relative min, 4, and whatever I get when I plug 4 into the function, I think that would be 6.
And you plug that 4 into the derivative, correct?
No.
No, you
That's a
plug
point on the original function.
Okay.
When you're substituting x values to find points on the function, make sure you're substituting the x into the original function. I just realized I could have asked you on the second part for the x-intercept. After I wrote it this way, it's easy to see what makes that 0. What would make that 0? What makes a fraction 0? If the numerator's 0, so if you set x cubed plus 32 equal to 0, what would you have to do?
Cube root of 32.
Can you take the cube root of a negative number? Cube root, yes. Square root, no. So it would have been fair on the test If I had asked you for the x-intercept on that one, it's negative cube, or not negative, cube root of negative 32, comma, 0. And that's approximately, for graphing purposes, that's approximately negative 3.2.
So that would have to be on our answer.
If I ask you for x-intercept, which I would on that one because it's not hard to find, then you would put cube root of negative 32, 0. But for graphing purposes, you need a decimal approximation.
So
Okay.
you don't have to worry about the denominator, just worry about
We already know what happens when the denominator is 0. There's a vertical asymptote. All right. Continuing with the calculus. I think I'm ready to answer E, F, and G. I have to look at the second derivative. So second derivative, I have that written down. It's 192 over x to the 4th.
We just use quotient rule to get that, right?
Yep. I just used quotient rule on the first derivative.
Use a shortcut.
What do you know about the sign of 192 x to the 4th? It's always positive, except for at 0. At 0, it's undefined. So how can I write that? Yeah, I'm going to write that. That's greater than 0 for all x not equal to 0.
So that's your domain.
Domain was for the original function.
Would we have to have two domains though for the derivatives?
No, we're not looking for domain now. We're looking for critical numbers. Does this have a critical number? Yeah, nothing makes it 0, and the only thing that makes it undefined also makes the original function undefined, so there are no critical points. And now we can answer questions about where the function's concave up, where it's concave down, and where there are inflection points. Where is it concave up?
Everywhere in its domain.
Everywhere but 0. I can't say it's concave up at 0 because it doesn't even exist at 0. So here I do need to write these intervals separately. Negative infinity up to 0, not including 0. And then 0 to infinity. Where is it concave down? Nowhere. What about inflection point? If the concavity doesn't change, there are no inflection points. So let's finish this graph. The y-intercept is negative, not the y-intercept, the x-intercept is negative 3.2. The relative min is 4, 6. Which, because of my poor spacing, it's hard to tell which side of the slant asymptote it's on. Yeah, but it's supposed to be up there. Oop, you can't see it. I know it's above the slant asymptote because what's the equation of the slant asymptote? That's all the points where the y is the same as the x. The ordered pair 4, 6, the y is bigger than the x. So it's above that line.
Don't you have a point at 0, 4?
I don't have any point on the y-axis. There are no y-intercepts. The function's decreasing on 0, 4, but that's an interval, not a point.
Yeah. Okay,
So do I know any other points? That's a relative min right there. And no points of inflection. The function is increasing from negative infinity to 0, and it has to go through that x-intercept. It's increasing and concave up. Can you do increasing concave up and through that point, approaching the vertical asymptote? That's the best I can do.
Increasing and concave up is hard for me.
Decreasing and concave down used to be, no, decreasing and concave up. When increasing and concave and concavity are different, that used to bug me. Actually, Sarah, if you'll hang on to that thought just a minute, I will make you a note at the bottom of the page here. That might be helpful to you. Can you see what goes on to the right of the y-axis? Has to be concave up, but it's decreasing from 0 to 4. Can you make the graph look decreasing and concave up from 0 to 4? Bottoming out at 4, 6. And increasing and concave up forever after that. And approaching that slant asymptote.
I know this is kind of a dumb question, but tell me again why there is no critical number on the second derivative.
Because the only thing that makes it 0 also makes the original function equal 0. Definition of critical number is the function has to be defined there and the derivative not defined, or 0. Now, Sarah, that I think I'm going to have time to do one more problem, but that little note I promised you, let's do 4 quick sketches of increasing and concave up, and then increasing and concave down, and then decreasing in each one of those. Increasing just means going uphill left to right. Concave up means it kind of has that hold water curve to it. So increasing concave up, do your very best little piece of a function, but do it in pencil in case you have to erase it. Increasing and concave up. Kind of looks like the right half of the graph of y equals x squared. And then increasing concave down, take a stab at that. Going uphill from left to...
The left half of y equals negative x.
You're a genius. That's increasing concave down. What about decreasing and concave up?
The left of x squared.
Decreasing and concave up. Yep. and decreasing and concave down. Now, actually, I love it when I'm thinking of new ways to explain things, but this just struck me as perhaps helpful. If we graph y equals x squared and y equals negative x squared, what do we have in the first quadrant? Which one of our four down here? Increasing concave up. What about the left half of y equals x squared? Yep. Third quadrant? And fourth quadrant? Decreasing and concave down. I've never thought to write it that way before. I like that.
What was our final graph of 12?
Final graph of 12. That.
Do we not have another part underneath it?
Let me think. You always have a part of the graph to the left of the vertical asymptote and a part of the graph to the right of the vertical asymptote. Miss Sarah, I'm not going to be able to erase it after I do it, but if I had anything over here, why is that not possible? And here's your hint. If I had anything down here, it wouldn't pass the vertical line test. It wouldn't even be a function. This is going to keep getting closer and closer to that intercept, but it's going to go forever to the right, which means there can't be any other point forever to the right.
You said you have one left and right of...
But the vertical asymptote is this. This is what's going on to the left of the vertical asymptote. That's what's going on to the right of the vertical asymptote.
Left and right of the slant asymptote.
Correct.
Okay.
Correct. Train your brain to look at rational expressions. What's going on to the left of vertical? What's going on to the right of vertical? All right. We only have time to do one more, but remember that the examples in the book are really good. And you may be thinking, how can it look harder than that? Well, they use these big tables, and the first time I taught this section, I made those big tables and put them on the handout, and finally I realized the tables were wearing me out. So I stopped. But you can look at them and see which you like best. The one I want to do super fast, number 46, just because it has arctangent and natural log in it. Yes, it is 44 in this book. It was 46 in the 4th edition.
Should we start a new page? It's gonna be long.
Yeah, I would think every one of these is going to take its own page. The homework, in case Siri or whoever that is cuts us off, the homework is exactly what's on the assignment sheet that I gave you the first day of class. It's 7 problems. And if you've lost that sheet, you can print it again in Momentum. All right. What about domain? Can you take the, is there anything, let me ask it this way. What kind of values can you take arctangent of? Or if you think about the graph of arctangent, how far to the left, how far to the right does it go? Forever. Arctangent kind of looks like cube root of x. It's forever to the left, forever to the right. So that part has a domain of negative infinity to infinity. How about this? This logarithmic function, I know I can't take the log of anything negative or 0, but if you think about this a second, that there's no way that's going to give you negative or 0. If you use the quadratic formula and try to find what makes it less than 0, there is nothing that makes that less than 0. Actually, yeah, no, that's right. So the domain is negative infinity to infinity. And that's number 1. Number 2, how do you find y-intercepts? Let x be 0. If I let x be 0, I would have 7 arctan 0 plus 1 minus natural log of, that would all boil down to just natural log of 2. What is the angle whose tangent is 1? And it has to be an angle between negative pi over 2 and positive pi over 2. The angle whose tangent is 1.
Pi over 4.
Pi over 4, where x and y are the same thing. So this is 7/4 pi minus natural log of 2. That's the exact y-intercept. But when I go to graph it, I'm going to need a decimal approximation. I already have it. It's about 4.8.
So it'd be 0, 4.8, right?
Yep. Number 3, I want asymptotes. Well, since the domain is negative infinity to infinity, we've already established you can let x be anything. There are no vertical asymptotes. And our theorem on horizontal asymptotes and slant asymptotes only refer to rational expressions where the numerator is a polynomial and a denominator is a polynomial. So there aren't going to be any asymptotes.
Arctan, though, has that horizontal asymptotes.
Hang on to that thought just a minute. You're right. Arctangent has horizontal asymptotes. Natural log doesn't have horizontal asymptotes. In order for this to have a horizontal asymptote, not only does arctan have to have a horizontal asymptote, but this minus that always has to be approaching some number as x's get infinitely big, infinitely small. And I think that's what doesn't happen. I may have to take that back in a minute, but that's what I think. Number 4, we're ready for derivatives, and this is actually kind of cool because I remember the formula for the derivative of arctangent. It's 1 over 1 plus ugly squared. And the derivative of natural log of ugly is 1 over ugly. Times the derivative of the ugly.
Your conference is scheduled to end in 2 minutes.
I'm going to go ahead and tell you what that cleaned up to be. It took a few minutes, but it cleaned up to be negative 2x plus 5 over x squared plus 2x plus 2. Sorry. And at this point, maybe I could scan this and put the rest of it in momentum for you. But the only thing that makes the original expression 0 would be 5/2. So 5/2 is your critical point. I would put it on a number line and figure out where the function's increasing, where it's decreasing, where they're relative max. You're not going to have time to copy all this down, so I'll just scan it and put it in momentum. It'll be there by the time you get back to your card. Then I found the second derivative and possible inflection points. I put them on number lines, and I found out where it's increasing, decreasing, concave up, concave down, relative max and min. It did a pretty good job of giving us a very accurate graph. Very accurate graph.
Decimal points, are they approximations or are they exact?
Those decimal points are decimal approximations. Yeah. So the homework, if she cuts this off, I've already put it in your hand. It's right. Here's my finger.
Your conference is now over. Goodbye.